Now to prove the other conditions, which is to show that phi is 1-to-1 and to show that phi is onto, we need to just define what 1-to-1 and what onto means and show that our map satisfies those conditions. For a map to be 1-to-1, phi of g raised power I equal to phi of g raised power j it implies that g raised power I is equal to g raised power j. That's what 1-to-1 means. That means if we have any mapping where, let's just say, this is pretty much what 1-to-1 means. If f of a to b is 1-to-1, that means f of a equals f of b implies that a is equal to b. And since our a and b here is gi and gj respectively, we need to prove that this implies this. So let's start from the forward statement. If phi of g raised power I is equal to phi of g raised power j, that means h raised power I is equal to h raised power j, since we already defined the map to be this, right? And if h raised power I is equal to h raised power j, that implies that I is equal to j. And if I is equal to j, g raised power I is equal to g raised power j. Since we have shown that this implies this, phi is 1-to-1. And for phi to be onto, if a map f that maps to a is onto, that means f of a is equal to b. Let's make that small letter b for a in a and b in b. That's what onto means. And just by the definition, how we define the map is obviously onto. So if h raised power m is in big H, then there exists g raised power m in G such that g raised power m is equal to h raised power m, and we know that that is true because phi of g raised power I is equal to h raised power I. So phi of g raised power m is equal to h raised power m. Hence phi is onto. And since it is a homomorphism, it is 1-to-1 and it is onto, we have proven that phi is an isomorphism. It's supposed to be an isomorphism. Therefore, G is isomorphic to H, and that's the answer to the question.